Continue.
So it's a great pleasure to introduce today Professor Giorgio Torrieri from the University of Campinas from Brazil. And today he will talk about ideal hydrodynamics and its extensions, fluctuations, polarization, and gauge theory. So with this, I now give you the floor. So.
Thank you very much. I really appreciate the opportunity to talk here. I mean, I do not know your background. And first of all, a warning. I mean, I will mostly introduce the field the way it's usually understood, but my topic of research might be a little bit unusual in the field. I won't even talk about this in detail because there's all these papers that you guys can read. I will sort of ask some questions and I will give my answers to these questions. My talk is very highly modular and you can interrupt me at any time. And if I don't talk about something, it's absolutely okay. I prefer this with a substantial discussion than, you know, going through 140 slides, which isn't going to happen anyway in 1 hour. And, you know, you don't understanding anything. There is like less than 10 people or close to 10 people. So by all means, talk. Interrupt me because I don't follow the chat. So just interrupt me. So I'll talk about sort of the Lifshitz and Landau introduction to relativistic hydrodynamics. I will introduce some things where I think warrant a rethink of how the whole hydrodynamics is defined. And I will talk about the approach via effective theory based on symmetries, which for those who've studied, for example, QCD, is similar to doing chiral perturbation theory. Writing all terms allowed by symmetry and sort of ordering them according to some gradients. And then I'll talk about, which is a good method, but it has its limitations. And then I'm going to talk about the method I'm developing, which hopefully will overcome these limitations. And these limitations are basically how to account for fluctuations from deviations from sort of the ideal thermodynamic limit in a system which seems to behave like a good fluid. In the beginning, I'll talk about why this is, in my opinion, the holy grail. So, I mean, I'm a particle physicist. First of all, the basics. And the first basic is I'm a particle physicist. Why am I even interested in hydrodynamics? Well, the reason I'm interested in hydrodynamics is because way back in 2004, there were these amazing news that scientists at the Relativistic Heavy Ion Collider, which is the collider which was tasked to find quark-gluon plasma, to find the phase transition in nuclear matter to a deconfined system. Instead of signals of a phase transition, it found signals of merely ideal hydrodynamic behavior in nuclei, which sort of became big news. It was written in all the newspapers. There were even coffee mugs being sold, which I have. So what does this mean? Well, I mean, if the system was more or less in equilibrium, but not strongly interacting at every point, it would produce particles that would simply fly out. I mean, maybe they'd thermalize a little bit, but they would evaporate. The system would just evaporate and the particles would fly out. And in flying out, they wouldn't know anything, if you want, about where they were emitted from. Was the place where they emitted from a hot spot with more particles? Was it a cold spot with less particles? It wouldn't matter. On the other hand, in the fluid limit, you have pressure gradients. If there are more particles, the system is hotter. If the system is hotter, it has more pressure, and pressure is a force, and therefore the momentum of the particles will be sensitive to the force gradients. And considering that you have two nuclei colliding, the hot region is an ellipse. The way to see if there are gradients of knot is by measuring azimuthal gradients in momentum, which experimentally is also sort of an easy way to, you see the reaction plane and you see whether particles perpendicular to the reaction plane are faster than particle parallel to the reaction plane. And they did, and it turns out that indeed they are. It seems to reflect very well pressure gradients that you can calculate from sort of initial conditions. And in fact, I mean, interpolating in between these two regimes, you have viscosity, which transforms gradients into heat. And it turns out that even a big viscosity, even a viscosity of 10% with respect to the entropy density, viscosity in natural units, which I'm going to use, H equals C equals K equals 1. In these units, viscosity has the same units as entropy density, so the ratio is a pure number. If this pure number is as big as 0.1, the data is not described. So viscosity really has to be small. At the same time, string theorists came out with the viscosity of the infinitely strongly coupled theory, which is comparable. It was conjectured to be the lowest viscosity possible in any material. So this is really exciting. And this is why this stuff made the news. Made the cover of PRL, and of course there was BBC, Space Daily, whatever else. And this also attracted theoretical interest to relativistic hydrodynamics, which was there, but it really became a hot topic. It really became a hot topic. So what is relativistic hydrodynamics? The first version of these equations was built by Landau and Lifshitz, and like everything else in their book. We can start by asking ourselves, hydrostatic, what does the energy momentum tensor look like at rest? What does the energy momentum tensor look like at rest? Well, it looks like this. The 0, 0 term is the energy density, the diagonal terms are pressure, the diagonal terms are all equal, and everything else is 0. Of course, the system is not at rest, but that's just a general Lorentz transformation in terms of 3 more parameters, which are flow. And the general energy momentum tensor looks something like this. It's E plus P, which is the relativistic entropy, times 2 flow vectors, minus P times the metric. And if you have a conserved charge, remember, most of the stuff conserved charge is an afterthought, because in the relativistic limit, I mean, that's one of the things that makes the non-relativistic limit from the relativistic limit so tricky. In the non-relativistic limit, you always have a chemical potential much bigger than the particle mass, because you have a particle density. In the relativistic limit, you can make a fluid with just with energy. Basically, the number of particles and the number of antiparticles is the same. So the conserved charge might be there, but might also not be there. And in heavy ion collisions, usually chemical potential is small. But anyway, in the ideal fluid, the energy momentum tensor looks like this in terms of energy and pressure. And if there is a conserved current, it's simply a density times a flow vector. It goes in the same way. And this is really nice because you have 4 equations or 5 equations with a conserved current with 4 unknowns. Why 4 unknowns? Because you have 3 flow components. The 4th component is a normalization. Then you have energy density and pressure, but energy and density and pressure are also related by the equation of state, which, PV equals nRT or something like that. So you have 4 equations and 4 unknowns, or with density 5 equations with 5 unknowns. You have any initial condition and a fast computer, and you can propagate. So it becomes a solvable system. Just conservation laws make the system solvable. And this is done purely from the hypothesis of perfect local equilibrium. That's what reduces the number of equations to the number of unknowns. Analytically, of course, you cannot solve these. I'll talk about it later. It's actually the general solution of these equations is one of the great mysteries of mathematics, but numerically, who needs analytics? We have computers, right? All good. What are all good? I mean, what have we done? What we've done is that we've approximated that the system is so strongly interacting that everything is in equilibrium. And also, it's a relativistic system, so everything is isotropic. I mean, the second thing, you might have strongly interacting systems which are not perfectly isotropic in the non-relativistic limit, but in the relativistic limit, because of how Lorentz transformations work, strong interaction and isotropy kind of might go hand in hand, and so the two are actually related. So we've assumed everything equilibrates fast. If you take this stuff and shake it, the energy of the shake becomes thermal energy instantaneously. And then we can solve the system. Obviously, nothing is instantaneous. Or is it? I mean, is there a quantum limit to equilibration? Something like this? We don't know. So maybe there isn't. And if there isn't, we can solve, and therefore we can compare to experiments. It's a very nice solution. What about entropy? Well, if you use the Gibbs-Duhem relation, you will find that if there are no shocks, entropy is conserved. There is a 3-line derivation that these 5 equations and 5 unknowns, assuming the equation of state really is the equation of state at equilibrium, is equivalent to entropy conservation. So all good. If there are shocks, this becomes more complicated, but again, shocks are a discontinuity, and we are assuming that the equilibration rate is much smaller in natural units than the shock profile. So that's okay. If this is happening, then entropy is conserved. So we kind of hope that hydrodynamics works in heavy ion collisions because we want to study the equation of state of quark-gluon plasma. We want to study deconfinement. When does the gas of heavy nuclei, heavy protons and neutrons and mesons, become a gas of practically massless particles? This is an equation of state thing. And the equation of state, to be sensitive to the equation of state, we are assuming a degree of equilibration. So we hope that hydrodynamics works. But according to QCD, according to asymptotic freedom of QCD, after deconfinement, the coupling constant should be small. If the coupling constant is small, the mean free path is big. So maybe there is some kind of equilibration, but should there be equilibration on a scale much smaller than the collision system for heavy ions? So thermodynamics is equilibration sort of in the volume. Hydrodynamics is equilibration at every point in the volume. And we were kind of hoping for the first, and we found the second. And this is not really explainable in the weakly coupled system. So maybe quarks are deconfined, but they still keep strongly interacting. And the question is, how strongly? And how do you parameterize this? Well, what happens, I mean, so the question is, what if there is a mean free path? How do we parameterize deviations from ideal hydrodynamics? How do we parameterize deviations from ideal hydrodynamics? Well, we can always find the flow. We can always find the flow just by diagonalizing the energy momentum tensor. Every energy momentum tensor, except like an electromagnetic field, will give us some kind of flow because it's a 4x4 symmetric matrix, and 4x4 symmetric matrices can be diagonalized. They'll have a real eigenvalue, which is the energy density, and it will have eigenvectors, which are the flow. So this you can always do. However, if you take this energy density and this flow vector and use them to construct this energy momentum tensor here, you will not get the exact energy momentum tensor because equilibrium probably isn't perfect. So one thing that you can do is to diagonalize the energy momentum tensor, find the flow, find an energy density, construct an energy momentum tensor, and call everything else, which by geometry is perpendicular to the flow, pi nu nu, the non-equilibrium part of the energy momentum tensor. So the total energy momentum tensor is the equilibrium part plus everything else. How do you characterize everything else? Well, we know that there must be some kind of second law of thermodynamics. So the entropy current better be above 0. You will have entropy created. By geometry, it will be perpendicular to flow. It has to be because flow is the eigenvector of the energy momentum tensor. So everything else which is not constructed out of that eigenvector, it's perpendicular. Of course, there are multiple eigenvectors, but usually only one is sort of physical. So that's before you ask. So that's good. So what happens if the theory is close to equilibrium? Well, if the theory is close to equilibrium, then this pi mu can only be sensitive to gradients. Can only be sensitive to gradients of energy density and gradients of flow. Can only be sensitive to gradients of energy density and gradients of flow, right? Because otherwise the system is not otherwise it's not equilibrium values which determine the system, and then you're really far away from equilibrium. And so let's take the gradients. If you don't have chemical potential, you only have gradients of energy density, right? So you can take the gradients of the energy density. You can take the part which is perpendicular to flow, and you can divide it into the traceless part, which transforms as a rank 2 tensor, and the trace, which transforms as a Lorentz scalar. By Lorentz symmetry, these are the only possible decompositions. These are the only possible independent decompositions. So your coefficients are going to be one coefficient which is proportional to the rank 2 tensor, and the other coefficient which is proportional to a scalar. Both, because of the fact that entropy has to increase, both coefficients have to be negative. So they have to resist gradients. They have to resist gradients. Physically, they are frictions, right? Physically, they are things that make the gradients go to 0. So the coefficient which is proportional to the rank 2 tensor is called shear viscosity, and the coefficient which is proportional to the scalar is called bulk viscosity. Physically, shear viscosity is stickiness. You have physically, shear viscosity is friction. You have a gradient of the fluid, and the coefficient transforms this gradient into heat. Bulk viscosity is stickiness. You make the system expand, and you have a residual resistance force. You make the system contract, and you have a residual resistance force. You have a residual resistance force. It's the resistance to dilatations, conformal transformations. And of course, if the system has no intrinsic scale, then this part should be 0. The coefficients of these gradients are things that can be calculated from equilibrium. The coefficients of these gradients are things that can be calculated from equilibrium, and they're known as shear viscosity and bulk viscosity. They also exist in non-relativistic physics. If you have conserved currents, things become a little bit more complicated, because in the ideal limit, from the non-decrease of entropy, you can understand. Yes.
Quickly. So the just normal resistance to flow, that kind of viscosity would here be the shear one. Just if you're wanting to flow the fluid to somewhere.
The resistance to gradients would be the shear viscosity. Yes.
I see. Okay.
The flow gradients. You see what I mean? I mean, obviously, if the whole system is boosted, shear viscosity has no effect. But flow, which is why this observable of the azimuthal gradient is so sensitive to shear viscosity. You understand?
Okay. Yeah. Thank you.
Sure. So what about conserved currents? Well, in the ideal limit, the current is proportional to the entropy current, because otherwise you would have entropy of mixing. If you are away from the ideal limit, things start becoming considerably more complicated, also conceptually, because the entropy current and the flow current and the conserved quantity current do not have to be parallel. You will have a vector of the difference. This vector can only be dissipative, because otherwise entropy will increase, otherwise entropy will decrease, entropy of mixing. However, what exactly is dissipating? Because now, we don't have a unique definition of flow. If you define U mu as entropy flow, this is what's known as the Landau frame, you will have diffusion of the number of particles. And you have to be careful because entropy is not conserved. So you have to divide changes in entropy from the conservation from changes in entropy from flow definition. If your flow is the current flow, this is known as the Eckart flame, you will have heat diffusion, and entropy will be created by the heat diffusion. And this is actually something which is, and this is something that should make you think, because you always think of a fluid velocity as something physical. But in relativistic fluids, there is at least two definitions of fluid velocity. What about in between? I mean, is fluid velocity something unique? In a perfect fluid, it is, because everything moves in the same direction. But in an imperfect fluid, there is an ambiguity, and you have to think about it. Fine. However, I mean, assuming that you know shear and bulk viscosity, and I will tell you in a few slides how to calculate it, I'll tell you in a few slides how to calculate it, you can linearize the theory, and which basically means you take a hydrostatic limit, a sort of chunk of fluid in equilibrium, and you put in perturbations in pressure, energy density, and velocity, or particle number, or what else can it be? And when you perturb it, you will find that you will have the relativistic wave equation. There will be a real propagation, which is the sound speed. There will be a real propagation, which is the sound speed. And there will be an imaginary propagation, which is the diffusion due to viscosity, due to shear and bulk viscosity. This diffusion will give you a sound wave dissipation length, which, I mean, this diffusion will give you a sound wave dissipation length, and I'm really sorry, in these equations, they're not dimensionally correct for people who should notice, because there is a factor of temperature underneath. There should be a factor of temperature underneath. Higher frequency waves, higher wave number waves diffuse faster. Higher wave number waves diffuse faster, and there is a k squared, and therefore there is an extra sort of length, which is 1 over temperature, and indeed there is a factor of 1 over temperature there. So the sound wave dissipation length is viscosity divided by entropy divided by temperature. But those who are following already see that there is a very big problem here, because k can increase to whatever you want. And phase velocity or group velocity are omega over k, or d omega over dk. So velocity can increase to wherever you want. So velocity can increase to whatever you want. I'm sorry, I just wanted to, there was this transparency should have been there first, I'm sorry, before sound waves. I mean, what the sound wave formula gives you is also a linear response definition of viscosity. How would you calculate? How would you calculate the shear and bulk? How would you calculate these two shear and bulk viscosities? Well, the linearization, the definition of the sound waves, actually gives you a way, actually gives you a very nice way, because you can take a hydrostatic system, perturb it at infinity, perturb it at minus infinity, and if you calculate the correlation function, you will find that the leading order coefficients are going to be proportional to the bulk and shear viscosity respectively. There should be the imaginary part of this correlator. This isn't just the correlator, this is the imaginary part of the correlator. And this is very nice because you can link shear and bulk viscosity to fundamental field theory. You can take a field theory in practice on the lattice. It's very difficult to do. Even perturbatively, you have divergences all over the place, but at least in principle, you can calculate using finite temperature field theory, the shear and bulk viscosity by calculating the correlator between two energy momentum tensors and taking the imaginary part and taking the leading order coefficient, infrared coefficient of the imaginary part. It's difficult in practice, but it's well defined in theory. The problem, of course, is that it's well defined in Euclidean theory, but in Minkowski theory, you have to be very, very careful because of this diffusion thing. In Euclidean theory, this propagator is very well defined because there is no speed of light, space equals time. Here, you have to analytically continue to get the Minkowski space, and you have a problem with analytical continuation because of this infinitely propagating diffusion wave. You have a k squared. You have a k squared. The diffusion speed is quadratically in k, and the diffusion is quadratic in k, and the wave and the group velocity are, and the phase and the group velocity are omega over k, which means they can be as big as you want. Physically, if you take a hydrostatic limit and you plot a delta function in energy in the middle, you will have a diffusion tail which will instantaneously propagate to infinity. You will have a diffusion tail which will instantaneously propagate to infinity, which is obviously non-physical because the system would be non-causal. So what do we do with causality? Well, the intuition from this delta function example is we add a speed to the diffusion of the tail. What this means physically is that friction is not instantaneous, and once you turn on the gradient, there is a time scale. There is a time scale for the friction to turn on. There is a time scale for the friction to turn on. This is known as the Maxwell-Cationic equation. It's very easy to sort of put it into linear order, and it's going to be a term which is second order and time gradient of tau pi, so that there is two gradients in time, two gradients in space, and so you can adjust the relaxation time so that the propagation is causal. The nonlinear equation for this is what is called the Israel-Steward equation, and it's going to be something like that. It's going to be the contracted gradient, and the contracted gradient is going to be the source of the contracted gradient is the Navier-Stokes pi mu nu. So on the left-hand side is the relaxation term. On the right-hand side, you have gradients of flow. However, what you've done is actually qualitatively new, because now this pi mu nu is 6 additional degrees of freedom. Actually, no, it's 10 additional degrees of freedom if you consider shear and bulk, that you have to solve from initial conditions. These degrees of freedom have diffusion type dynamics. They have this relaxation equation, but they are still degrees of freedom. They require new evolution equations. And this is another place where I want you to stop and ask questions, because how many degrees of freedom do we really have? Is this pi mu nu physical? How do we measure it? If you look at these equations, it looks like it's a physical quantity. You perturb the energy momentum tensor, and you perturb the energy momentum tensor, and you watch this perturbation decay. But I've told you a few slides before that flow is not uniquely defined. So this perturbation here, you can rotate in flow space, and you can call it a sound wave which decays. One observer is going to call this pi mu nu the dissipative part of the energy momentum tensor, and it will have a relaxation type equation. Another observer will change u mu to something which is more proportional to the entropy flow, and they will simply call this a decaying sound wave. Who is right? Are we overdetermining our system? This is another question that I would like you to ask. And also, just if you're a numerical person who wants to solve these equations and get data to compare to experiment, the number of equations becomes 16 equations with 16 unknowns, and they're all nonlinear and really complicated. So it really becomes really important. And if you're a theorist who calculates things from first principles, then now you have this tau pi that you have to calculate from first principles. There is a Kubo formula for it as well, but it's the second order coefficient of the sound wave. And there is, if you want to go to the same order in gradients, you will have something like 20 new transport coefficients to calculate. So basically you have a job for life. But sort of conceptually, there is an ambiguity of how many of these coefficients are physical and how many of these coefficients are redundancies, or things that you define in a certain way that would go away if you redefine them. And this is sort of the, and this is where we come. And so the question is, how universal is this theory? What is the physical meaning of the different formulations? What is of the different formulations of hydrodynamics? And recently, people have taken this to heart. For example, there is the so-called BDNK, Noronha, Visconti, Benfica, Koftun. But this is actually a rediscovery of things that general relativists were doing like 25 years ago, Georg, Hitchcock, and Lindblom, who are making, who have a frame in between Landau and Eckhart in such a way that these second order terms are either small or even zero, in such a way that most of this non-equilibrium part is reabsorbed in gradients. So we don't know how universal this is. We don't know how universal the transport coefficients are. There are several versions of hydrodynamics. And recently, you have the question happens, well, okay, but even in relativity, there are ways of breaking isotropy. You can add spin, and you can add spin, and you can add gauge symmetries. Let me just, is spin, I mean, who cares about adding hydrodynamics to spin? Well, this was the last enormous experimental result of heavy ion physics. Lambda particles decay using parity violation, so you can measure lambda spin from the spatial distribution of decay products. And our experimental friends have done this, and they found something incredible. Remember our heavy ion collision, you collide it, the off-center collision produces azimuthal gradients, it also produces vorticity, right? If you solve hydrodynamic equations, you have vorticity. So you can predict the vorticity direction, and you can measure spin polarization in the direction of vorticity, and you found a positive result. This is amazing. It made the cover of Nature, and it should have. It's a really amazing discovery, and it repeats a discovery made in cold atoms. People have made strongly interacting cold atom systems, made them spin, and they found that the polarization of these cold atoms that they measure with magnetic fields is proportional to the vorticity. So if you're an experimentalist, you can go away and you can congratulate yourself because this is amazing. If you are a theorist, you really have to think again, because now we find that vortices, we find that the system is very strongly interacting, but for example, vorticity is not conserved, cannot be conserved, because some vorticity goes back, reacts into spin. You have microscopic degrees of freedom and macroscopic degrees of freedom talking to each other. And the microscopic degrees of freedom are not isotropic because they carry spin. What the hell is the ideal relativistic limit of that? No one knows. Actually, maybe me and David Montenegro know, because we have a proposal about this, but it's an extremely controversial topic in fundamental physics. There is no agreed definition of hydrodynamics with spin. It gets better. If you remember electromagnetism, I mean, we've measured lambdas, but we think there is a quark-gluon plasma, so gluons and quarks are polarized. And now you have a problem. Now you have an even bigger fundamental problem, because gluons are gauge invariant. And gluons have 3 possible spin components, but only 2 are physical. Longitudinal spin is a gauge-dependent quantity. It's unmeasurable. Only the transverse spin components are measurable. But vorticity can go in any direction. Vorticity is not gauge dependent. So how do gluons transmit polarization? If gluons are microscopic components, vorticity is sort of a collective excitation, and they talk to each other. The collective excitations are always gauge invariant. The microscopic excitations are gauge dependent. There is an ambiguity. I'm asking these questions, and I'm actually sort of close to the second half of the talk, We have proposals to solve it. You can read my papers, but I would be unfair if I told you that this is the right solution, because there is the conferences on this field are very nice, because they're really meetings where people don't have a clue, and people who say that they have a clue are lying. They're overselling their work, because this is a really fundamentally not understood subject. How does spin propagate if you're close to local equilibrium? Yeah.
So can I ask something? So the fluids produced in this collision where the vortex coupled to the spin, are those charged fluids or uncharged?
They are in heavy ion collisions, to a very good approximation, they're not, because you have as many particles as antiparticles. You do have a little bit of charge, but it's a small correction.
So the coupling that you're talking about is
color.
So it's not a fundamental electromagnetic coupling either. It's
no. If it was, viscosity would be ginormous.
Right.
Like on the nuclear scale, the mean free path.
Right.
Yeah. Of course, they do have color charge. So if vorticity is really transferred to polarization, it's transferred via chromomagnetic spin-orbit interactions. But I mean, the microscopic details, if you're close to equilibrium, should be irrelevant, right? Everything should be in local equilibrium.
Right.
The problem is, what is local equilibrium here? Because you have vorticity. What is local equilibrium here? Because you have vorticity, and vorticity is sort of non-local with respect to the mean free path, right?
Right.
Yeah. So it's an even more basic problem. You see what I mean? Yeah. So last but not least, can we say anything? I mean, I said that we can calculate shear and bulk viscosity and eventually relaxation time using Kubo formula from fundamental theory. But it's extremely difficult to do in practice. In QCD, you have divergences and resummation, which screw this up. On the lattice, you have to take an infrared limit of a lattice result, so this is really complicated. So for realistic theories, this is still work in progress, and this is a technically formidable problem. This is technically really a formidable problem. Are there at least limits that one can make? Well, in the 80s, there was this really amazing paper by Mikhail Gulashi and Pavel Danielewicz, who did this sort of back of the envelope calculation where they say, well, let's take the Boltzmann equation, where you can calculate the viscosity in terms of average momentum, density of degrees of freedom, and the mean free path. And let's say that the mean free path, and let's say that the mean free, how big can a quantum mean free path be? Well, because of the uncertainty principle, it cannot be smaller than the average momentum, right? If it was, we would be able to make sort of a wall of this magical, strongly interacting stuff, and we would violate the uncertainty principle. So if you plug this in, you will get a viscosity over entropy density, which is roughly 0.1. But obviously, this is sort of a back of the envelope estimate. We don't actually know how to, because for a strongly interacting system, where the mean free path is close to the uncertainty principle, correlations become a big deal, and quantum correlations, as many of you know, are extremely non-trivial. So this is a back of the envelope estimate where all assumptions are questionable, right? So what more we can do? Well, string theorists found this amazing thing called the ADS-CFT correspondence that relates an infinitely strongly coupled theory to a classical gravity. And using this, we can calculate the shear viscosity of a conformally invariant theory, which it's a theory with 4 supersymmetries and an infinite number of colors. So it looks nothing like physical QCD, but hey, its coupling constant is infinitely big. And there, it's actually a pretty universal thing because of the black hole no hair theorem. the equivalent of the Kubo formula, the equivalent of this Kubo formula for bulk viscosity is 0 by conformal invariance, so that's easy. Shear viscosity is you take a black hole and you shoot a graviton into it, and you see the probability of the black hole to come out, and this is basically the graviton to sort of come out of the black hole versus the graviton to be absorbed. And this is the Kubo formula. So there it becomes a trivial exercise. And by the no-hair theorem, the probability of the black hole to absorb the graviton is the area. The entropy density is also the area. So E over S is a fundamental constant, which if you plug in the numbers is 1 over 4 pi. So the Boltzmann equation gives you 1 over 10. String theory gives you 1 over 4 pi, which is basically 1 over 12. It's the same thing. And it seems to be the same thing that what the data gives. So that's amazing. I mean, there must be some extremely deep principle there that we have to find. Or not. Because these two theories are very different, but they're very similar in one very important way. They assume that the number of degrees of freedom is in some sense infinite. The Boltzmann equation assumes molecular chaos. It assumes that the collision term is factorizable. That actually means that the distance between degrees of freedom is parametrically smaller than the scattering length. That's the approximation that's made. ADS-CFT assumes the number of colors is infinite. So it's actually pretty much the same assumption. The number of particles is much, much bigger than the mean free path in both cases. Is this assumption true? Well, number of colors is the only thing we know for certain. It's 3. Right? So that we know. It's not true. Could it be that the mean free path is much bigger? Could it be that the system is still behaving like a fluid, but the mean free path is much, much bigger than the distance between degrees of freedom? And this is where experiment put a massive spanner. This is where the LHC turned on and put a massive spanner in the works here. Because they started seeing fluid-like behavior in even proton-proton collisions. And in fact, if you start applying the fancy schmancy analysis techniques that experimentalists have found, it actually seems, I mean, this is a controversial topic. You have to invite an experimentalist to give you the gory details, but it actually seems that small systems with 50 particles of 1 proton size and systems with 2,000 particles, which are sort of central lead-lead collisions, are just as collective as each other. So this assumption on which all these calculations are based is really bad with experiment. Is really, really bad with experiment. The number of degrees of freedom, the system does seems to be a good fluid. The number of degrees of freedom is small with respect to, the number of degrees of freedom is not big with respect to the mean free path. So this is, so we need to a fluid where we give up this assumption. Most people in the field don't really believe this because when you have a hammer, everything in the world looks like a nail, and most people still do either Boltzmann equation calculations or ADS-CFT calculations. And so they've started and they've largely succeeded in finding essentially very highly symmetric solutions which appear hydrodynamical but aren't. This is known as hydrodynamization, hydrodynamic attractors, and And they're very elegant solutions. And yes, it really looks like the system flows into, and it really looks like the system flows into something which looks really hydrodynamical. But the problem is that they're really symmetric systems. And also they're kind of, in my opinion, they're really asking the wrong question. because they're saying, well, the gradients are big, and the gradients are big with respect to the mean free path, and the system still flows to a hydrodynamic minimum. The gradients aren't the problem. The number of particles is the problem. Even if the mean free path is 0, at equilibrium, you're calculating the fluctuation as well as the average. You have to check that in every volume cell, the fluctuation goes to 0. So the probability starts to resemble a delta function. That's basically what's known as ensemble averaging. Molecular chaos is related to this. And it's certainly not true if the number of degrees of freedom is 50. So you have to think about what fluctuations do to hydrodynamics. And all of these approaches do not really know how to calculate fluctuations. And also, why did I mention polarization before? In a sense, polarization is an experimental proof that microscopic and macroscopic degrees of freedom do talk to each other. Microscopic and microscopic degrees of freedom do talk to each other. So, in my opinion, I mean, we're coming to the last 10 minutes. So let me give a summary. In my opinion, what is missing is, on the theory side, is making statistical mechanics, including fluctuations at the level of the partition function, compatible with hydrodynamics, which is a theory of averages. Statistical mechanics should be compatible with hydrodynamics, and at the moment it isn't, because every cell sort of flows. Flow is not well defined. Local and global equilibrium are very different beasts, and we don't know what the system looks like if fluctuations talk to collective excitations, which experiment says it's happening. The only way that this could work is if fluctuations somehow help to thermalize. Which in the beginning, and certainly when I first started thinking about this, it sounds crazy. Why should fluctuations help to thermalize? You have a fluctuation dissipation theorem. You have the fluctuation dissipation theorem. Fluctuation and dissipation are related. How can fluctuations help you thermalize? However, forget heavy ion collisions, QCD, and string theory. Forget even ultra cold atoms. Let's talk about nuts. Has anyone heard of the Brazilian nut effect here? I just wanted to mention it. I heard about it since last week. I'm asking a question because I'm genuinely curious. Have you guys heard of this?
Not the effect, no.
Not the effect. I mean, the nuts, well, no. So the effect is this. Sometimes it's called the muesli effect. Sometimes it's called the Brazilian nut effect. And the technical name you find on Wikipedia is granular convection. If you take a glass of nuts of various sizes, and you start giving it small shakes, small random shakes, not big shakes, but small shakes, you will actually find collective hydrodynamic phenomena. The most obvious manifestation of this is buoyancy. Brazil nuts always go up, and sort of smaller nuts go down. This is buoyancy. But if you keep track of the position of every nut, it turns out that they do even vortices form, and they do convective flow. This is actually still unexplained, and if you Google it, you will find papers in physics journals about this. So, before you start talking about QCD, here is a nice effect. And obviously,
can I ask something just from the picture alone? From the picture alone, it seems like mean free path is like 0, very, very close to each other, right? And
fluctuations are non-zero.
Yeah, and a lot of
fluctuations are non-zero, right?
Yeah.
You certainly cannot find and you certainly cannot model this by Boltzmann equation, because molecular chaos There is no molecular chaos here.
No, that's true. They are a fixed thing. Yeah.
Yeah.
Number of orientations is infinite each location. So like SUN kind of is there.
Yeah, sure. I mean, I agree. So all these things I said about heavy ions, you have an internal structure, you have big fluctuations, all these puzzles that I was talking about are similar. I do not know if the dynamics is the same. The dynamics could be very different. I do not know if the dynamics is the same, but it's just a very interesting thing to think about. You see what I mean?
Indeed.
I mean, yeah. And actually, I mean, my last transparency will suggest that it is actually the same. My last transparency will suggest that it is actually the same. But it's, I only found this out from a student like about a week ago. So this is, I mean, you know, it's just an amusing example. So the question, sort of the fundamental question that I leave you is, could fluctuations help lower the dissipation? And a sort of more formal question is, how does statistical mechanics with fluctuations really sort of come in with a theory of averages? So I only have 5 or 10 minutes. So I will just outline the things that I've been working on to answer this question, and everything we did is highly incomplete. So the first attempt at this was Lagrangian hydrodynamics as a Lagrangian effective field theory. So forget everything I said about T and U, put everything in the lab frame. The degrees of freedom are the degrees of freedom are the 3 directions of the fluid cell. But of course, there is a redundancy between these 3 directions because the ideal fluid is isotropic, then can go in every way. So you have actually local symmetries, and they are manifest themselves by the fact that the Lagrangian isn't directly a function of these guys, it's a function of the determinant of the volume. And it turns out you have a very funny Lagrangian because it's negative, but it's a function only of the volume element. You have a unique definition of flow, which is going to be the local gradient perpendicular to those. And if you've studied general relativity, this looks very, very, very similar. And indeed, hydrodynamics is a simplified general relativity where the local volume element isn't 4D Lorentz, it's 3D Euclidean. The metric, this funny phi I, the gradient of phi I. So the gradient of these volume elements is nothing else but the Vierbein. Here it becomes a Dreibein. It's not a Vierbein. The flow, what is called the flow velocity, is the Killing vector. And because it's not really general relativity, it's a simplified general relativity. The Lagrangian is only a function of the volume element times basically a cosmological constant that depends on the equation of state. The cosmological constant depends on the volume element. So it's a glorified de Sitter space. And indeed, I mean, that sounds very highly abstract, but you know that if you take a bubble of gas and you put it in vacuum, it will expand, and the solution was asymptotically approach an expanding universe type solution. I mean, Milne did this like 50 years ago when he did the Milne universe. So a simplified GR, so fluid dynamics can be constructed as a symmetric Lagrangian theory, and this works really well because it turns out that the Lagrangian has this effective dimensionful constant of the energy density, which acts as a Planck's constant, and you can define a functional integral non-perturbatively, and you can define a functional integral non-perturbatively. Solving it is another matter, but you can certainly define it, and you can calculate effective viscosities, including all fluctuations non-perturbatively. This way, it's possible to use dissipation. It's possible to use doubled variables to put in dissipation. And if you expand this around the hydrostatic limit, you will find that vortices and fluctuations actually give you singularities, because vortices will not propagate, but will stay. And therefore, if you evolve the system over time, the vortices will start accumulating, interacting, and therefore fluctuations do not average to the same thing. We've done everything possible with this theory. We put this on the lattice like 5 years ago. Then with the and also for the people who do many body quantum systems here, in field theory, the conserved currents, scalar conserved currents, are simply the Noether current of an internal phase. The Noether current of an internal phase. So we add an internal phase to the system, and this is really nice because the ideal fluid limit, where the current is proportional to the entropy flow, the ideal fluid limit can be thought of as a general covariance of the phase. So the phase is going to be locally covariant with respect to the coordinate. If you guys can put in a quantum phase and prove that using Eigenstate thermalization, this is an emergent symmetry, this is wonderful. I'm trying to do this, and we're still not there. But this would be a really great step in putting this Lagrangian theory together with statistical mechanics, since in quantum statistical mechanics we have the random phase approximation. So I would think this is a symmetry. But anyway, one thing that we did, we noted this. I mean, this singularity of vortices was noted before us. But the very, very nice thing is that it's very easy to put in extra constraints and extra symmetries, such as spin. And we did this, and we found that spin can act as a sort of Higgs-like mechanism to regularize vortices. So spin can act as a sort of soft energy gap to give a mass-like turn to the vortices, and this might be how you cure the instability of ideal hydrodynamics against vortex-type fluctuations. Eventually, you will have spin states, and this gives you a lower limit on the relaxation time. This gives you a lower limit on the relaxation time, which is determined by the polarization susceptibility and the equation of state. There is a lot of details here, and I could give another lecture about this, but I can't because we're out of time. So gauge theory will also give you an ambiguity in how the entropy current is defined because of the Fadeev-Popov ghosts, and we're sort of studying this. But just to tell you that spin and gauge symmetry can be accommodated by these Lagrangian hydrodynamic somatic symmetries. However, if you think about it, there is going to be sort of non-dissipative. There is going to be in non-abelian gauge theory. There is going to be a non-dissipative isentropic currents, which are sort of equivalent to what is called the falling cat problem. Just like a cat can always land on its feet. Basically because they can always choose a gauge in which they can land on its feet, and this can actually be analyzed using geometry. I mean, Frank Wilczek wrote about this. You might have an ambiguity in how global equilibrium is defined because of such isentropic states. However, a limitation of all this is the fact that this theory is based on coarse graining volume elements. So it cannot really tell you what fluctuations within these volume elements is like. You might be able to put them in as a source by hand, but you will not have an effective theory which will have microscopic and macroscopic degrees of freedom talking to each other. And hydrodynamics in small systems requires exactly this: how to link microscopic and macroscopic degrees of freedom. One recent way that I was thinking about how to do this involves the Zubarev statistical operator, for those people who know this. together, I mean, you basically take the density matrix and you write it in terms of and you assume that there is a local sort of near equilibrium operator. And so you can write the full density matrix in the basis of this operator, using the energy momentum tensor, And this will give you an equilibrium state, which includes all the fluctuations. This will not be the whole state. And you also need you will also need a quantum state to describe the residual. Remember the beginning of this lecture. You have the equilibrium state and you have the non-equilibrium state. And both of them have to be defined as statistical operators because both of them should include fluctuations. Well, the Zubarev approach could give you a statistical operator capable of describing the equilibrium state. And for those people who studied this, and I know some of you have done mesoscopic systems, so you probably know about this, you have something called the Crooks fluctuation theorem, which is basically that the momentum flow done on the system over the momentum flow being done by the system is the exponent of the ratio of the entropies. So the Crooks fluctuation theorem can be used to describe the away from equilibrium statistical operator. And both of these guys can be used to define a statistical operator for the full hydrodynamics, including the dissipative and the non-dissipative term. 3 minutes more. This is complicated. This becomes really complicated and non-local. In principle, it can be solved on the lattice. And it's going to be something like this. But one important statement is that if this is true, then indeed the non-equilibrium and the equilibrium state are not uniquely defined. And there is a sort of gauge-like transformation between them. In the beginning, I mean, when I was talking about conserved quantities here, I said that conserved quantities, where was it? Well, I said that conserved quantities can, sorry. When did I talk about this? I said in the beginning, I said that conserved quantities, if the equilibrium is not perfect, which also includes fluctuations, leads to flow being ambiguous. This obviously also includes fluctuations. And therefore, the choice of flow, the choice of equilibrium, and the choice of non-equilibrium are related by something like a gauge transformation. And the reason it's something like a gauge transformation is that its effect, if you look at Zubarev hydrodynamics, is exactly the same as the gauge transformation. You choose a gauge and you stick a delta function into the partition function to enforce this gauge choice, and you will have correlations between gauge invariant and gauge dependent fluctuations, which are in quantum field theory are called ghosts. And something similar might be happening in hydrodynamics, and the non-uniqueness of U mu means that equilibrium and non-equilibrium are not defined uniquely. And if you think about non-equilibrium statistical mechanics arising from sort of ergodicity, what this means physically is that small deviations from equilibrium could mean that some microstates are more likely than others because you are far away from equilibrium. But it could also mean that because of a fluctuation, you are misidentifying the flow vector. And in relativistic physics, flow sets a clock. So it could be that some microstates are not, that the system is really ergodic. It could be that the system is really ergodic, but you've misidentified the flow because of fluctuations, and the lack of ergodicity is because of this fluctuation and because of Lorentz time dilation. Which one is it? Well, the point of this gauge transformation is that the two should be indistinguishable at the level of every volume cell. And this makes the dissipative part of the system ambiguous up to fluctuations. And this might be the answer to what helps. And this might be the answer because of the fact that for small systems, for fluctuating in systems where the number of degrees of freedom goes to infinity, the probability of this happening also goes to zero. So hydrodynamics is a good theory of averages, and it's well defined, and you can forget about fluctuations. For water, this is certainly true. But for a quark-gluon plasma with 50 particles and for the Brazil nut type system, this might actually not be true. And paradoxically, it might be that, because of the fact that in this regime, the separation between equilibrium and non-equilibrium is not unique. It might be that there is a gauge choice which correctly describes evolution where the non-equilibrium part is really small, and the system looks like it's ideal hydrodynamics, but it's just that you've picked one of the many equivalent configurations to describe the system. And that's why it's happening. And this is why fluctuations counterintuitively might help you to thermalize. This is still extremely speculative. I mean, don't take it too seriously. This is a work which is still in peer review. It's the last of the papers I've put on archive. But I just want to say that it's still an open problem to make hydrodynamics and statistical mechanics compatible. And it's a very sort of abstract problem, but recent results in experimental heavy ion physics such as polarization due to vorticity, such as hydrodynamics in very small systems, particle systems, made this problem concrete. It's actually a problem that you need to understand experimental data. And in my opinion, sort of top-down approaches which have been used to derive hydrodynamics so far, such as the Boltzmann equation or gauge string duality, are incomplete exactly in this regime. And this is why I'm sort of trying to reinvent hydrodynamics as a field theory with high amounts of symmetry. Thank you very much. Yeah. Sorry for going slightly over here.
Oh, no worries. Thank you very much for this very intriguing talk. So we can maybe we can take far more minutes to one or two questions. So is there any question from the audience?
So have people taken some steps regarding this first point, right? Take a microscopic ergodic model, say of a spin model or something, and try to.
Not that I know.
Okay.
But look, I mean, this is a paper that we've put online in September. It's still under peer review, and there is quite a few people who are saying, "What the hell are you talking about?" You see what I mean? Okay. And the idea is still incomplete. I would like to do this. I would like to. I mean, this is where this actual. I mean. This is where I'm hopeful that this is where the not example might be. This is where the not example might be sort of relevant. I mean, because the point here. So why is the Brazilian not similar? They're being shaken, and this gives you randomness, and you kind of have to integrate their motion in an ensemble of results for shaking. Obviously, no one is shaking heavy ion collisions, but you have internal fluctuations in every cell. So you can think of elementary collisions as being in equilibrium. There is actually work on this. It's the Eigenstate thermalization hypothesis. I mean, this is work that goes beyond called heavy ion collisions. You have the so-called Eigenstate thermalization hypothesis, and you have hand-waving arguments that strongly interacting quantum systems are always look like close to equilibrium if you don't measure correlations too carefully, right? So your question is, let's divide the system. Your question is, let's divide the system into cells. Let's divide the system into cells. Let's impose eigenstate thermalization on every cell and put in fluctuations and sort of have an ensemble of trajectories and see if this looks like how likely is for one trajectory to look like an ideal fluid. This would be a follow-up project to our speculation, and I would like to test this. Absolutely. Yeah. Any ideas on how to put this concretely are very welcome. How to do this concretely are very welcome. Yeah.
And the connection with the micro and macro variable, you made a very brief mention to it, why spins might be coupled to the vortices, but it was, I think I missed that.
The connection is that spin is a microscopic variable. The connection is that spin is a microscopic variable and vortex is a macroscopic variable. And the two are mixing. They're correlated. So you have a macroscopic microscopic correlation. You are never going to describe this by a coarse-grained theory, by definition.
No. Okay, I see. So that is already, yeah. So I see only one analogy I know in the past is a bit like impurity spin and a Kondo cloud in some sense. Could be something like that. So
let me just mention one thing, which is sort of actually really controversial in our field now. That if you put in spin, the energy momentum tensor is not actually uniquely defined because you have something called the pseudo gauge transformation. This is in relativistic physics. If you add to the energy momentum tensor the gradient of any rank 3 totally antisymmetric function, absolutely any, you will get a conserved current. And there is actually a nice microscopic it's a generalization of angular momentum. And this is how, if you know general relativity, this is how you go from the canonical energy momentum tensor to the Belinfante-Rosenfeld energy momentum tensor. You basically choose the pseudo gauge transformation where it's totally symmetric. But the second term is antisymmetric, so you can add sort of antisymmetric parts. So spin is antisymmetric, and it's a microscopic observable, So the question is hydrodynamics with spin pseudo gauge dependent or not? And there are effective models where it's pseudo gauge dependent. My feeling was always, if you get a pseudo gauge dependent answer, your theory is wrong, because pseudo gauges are sort of a geometric thing. And this is controversial. It's fun. I mean, I really like this field because you can really formulate things that are related to textbook physics and people are arguing about that. You see what I mean? But what this tells you, I mean, this is where this coarse graining issue is important. What this tells you, is that it's not just a question of choosing a cell and integrating all over the cell. The cell has this spin structure, and fluctuations in this spin structure give you non-trivial macroscopic couplings. So you have to be very careful of how you coarse grain. In field theory, this happens, and the coarse graining, and for example, in field theory, gauge theory has to survive coarse graining, and in confining theories, you can do this by hadrons. In theories which are partially deconfined, you can do this by Wilson loops, which are non-local, by Polyakov and Wilson loops, which are non-local objects, right? So the coarse grain theory is a theory of non-local sort of Wilson loops. And I think of Zubarev and the Crooks fluctuation theorem in a similar way. That's why I think that they're the way to go.
Okay, thank you. Yeah, yeah.
Sure.
Okay, so since there are no more questions, we can conclude the formal part of the talk. So thank you very much again for this very intriguing talk. I really like the analogy with the Brazilian nut. So it sounds,
Same here.
I'm really curious to see what will come out of so what will be so how to explain this.
Sure.
Okay, so I'll thank you.
Okay, if you have any more questions, I can stay for a few more minutes. If you have any more questions formulated later, please email me. Marco knows my email address. Yeah. Yeah, but it was great to talk here. And please send me the link. If the link of the talk is publicly available, please send it to me.
Yes, yes, we will do that as soon as we're still in the process of making a website. So, but once it's online, then I'll send you the link.
Sure.
Absolutely, yeah.
In the UK, I mean, I could mention that one group that works a lot on very similar topics is Andrei Starinets group from Oxford University. They derive the effective, they started with ADS-CFT and they've been sort of deriving the effective theory of hydrodynamics using ADS-CFT as a help. In a sense, and I think they actually have this sort of fake equilibration type models using ADS-CFT. They also have ADS-CFT inspired analytically continued formulas for this stuff. So if you want to ask someone to give sort of maybe an in-person talk nowadays, they are the people who work on this. I think that the problem with this is that these objects here are not gauge, they're only gauge invariant if you take the hydrodynamic limit. So if you take the infinite limit and you stick an infinite number of particles between them, they're well defined. But away from this limit, this becomes gauge dependent, and this is the issue. They probably would disagree.
That is, I guess, these kind of very basic fundamental thing as whenever you want to do emergent physics and so have something very nice in emergent physics.
And actually, Marco, just to tell you, one of the sort of top people in the group is a Slovenian guy who recently moved back to Slovenia, Sasha Grozdanov. I don't know if you know him.
Yes. You mentioned it once before, yeah.
He's a really smart guy, and yeah, he would know a lot about this stuff. Yeah.
Okay. Thank you.
No, I mean, sure. This is, take everything I said with a grain of salt. From Landau, I mean, except for the first 30 minutes.
Okay. Yeah. So, yeah, we can end the Zoom, and yeah, I'll send you the link as soon as we have it online. I think we put it on YouTube quite soon.
Yes. Yeah, we'll upload it to YouTube so people can share it and send it off to anyone who couldn't get to talk, and then we'll send you the link once we've got the website up and going as well.
Sure.
Brilliant. Thank you very much, Giorgio. It was really
Absolutely.
Absolutely. Thinking about the
thank you.
This notion of it's now sticking with me. I think I'm going to go and play with it. But,
sure.
The difference between thermalization and local thermalization is interesting.
Look, if you have a jar of nuts, and just go and look at it, probably the bigger nuts are on top.
Yeah.
And if you think about it, why is this? I mean, it's because they were shaken. It's because they were shaken while you were bringing them to the kitchen from the supermarket or something like that. But there is no reason for them. I mean, this is buoyancy. This is a fluid. There is no simple explanation for this.
Well, I'm thinking again more in terms of the many body. Sorry, one sec. Let me turn on my camera. But this, because the eigenstate thermalization hypothesis is obviously quite recent. It's 2015 it really came into its own. So I don't know if anyone's really, and even then it's still a hypothesis. It's kind of an abstraction of the ergodic one. So
the first version of the eigenstate thermalization hypothesis is actually from the 70s. It's what's called Berry's conjecture.
Berry's conjecture. Yeah, this is the route that Nicky takes in his paper. He goes through Berry's conjecture.
Who?
Srednicki, am I pronouncing that right?
Srednitsky, yeah.
Srednitsky, sorry, yeah, Srednitsky, yeah. It's the route he takes in his paper. It's through Berry's conjecture. The modern incarnation is interesting. I don't know. I just never thought of that question before. The difference between thermalization and really small local thermalization, and whether or not they line up as you kind of scan out.
Sure. No, I know. That's that's the issue. Yeah. There is an imaginary sign on these operators, by the way. There's mistakes all over these slides. Yeah. All right.
No, thank you very much. Really interesting.
Thank you.
Thank you.
See you.
See you, Giorgio. Thank you. Bye.